So welcome back. And as our final plenary speaker of this workshop week, we have the pleasure of having our local colleague, Simon Griffiths from the Catholic University nearby. And he'll be talking about Ramsey numbers.
Thank you, Roberto. It's a pleasure to be here. Thank you to the organizers for the invitation. And you know, I know lots of people here, so it feels like a friendly crowd. Are you feeling friendly, everyone? Okay. Yeah. And you should feel, relaxed to ask any questions if something isn't clear. Or, I hope we have a nice interaction rather than just me talking a lot. I know the general vibe is there's more probabilists, so I'll try in a few moments say, probability has a very strong link with the whole Ramsey project and everything, so it won't be too difficult to touch on a few probabilistic things, even though our work wasn't especially, we throw in a bit of probabilistic combinatorics, but it wasn't especially. I also throw in a few AI art things just to kind of make a few nice pictures, because the rest of it's just me writing things, and I can't write this, so I've got to make it a bit more lively. Okay, so we start with the question of what is Ramsey theory. And I suppose most people have seen different, have heard about it in various contexts, but the main message that's common to all Ramsey theory problems is it's sort of the study of inevitable structure. So if you have a big enough object, maybe you can always find somewhere in there a little part that's very well ordered. And this shows up in a huge variety of different settings. In colorings of the integers, you can find monochromatic solutions to equations. This is a generalization with systems of equations. You can find collections of finite sums all in the same color, arithmetic progressions, subspaces, and there's many, many other contexts. So I'm just saying it's a really large and vibrant area of Ramsey theory that I won't be getting into. Because we're going to stick mostly to the case of graphs. Let's say who was Ramsey. So Ramsey, Frank Plumpton Ramsey, made contributions to philosophy, economics, and mathematics. Tragically, he died when he was only 26, I think in 1930 it was, and but managed to make huge contributions to 3 different areas, despite only living a very short time. And he used to say things like this: I hope you like red-blue colorings. So the theorem of his, which is most relevant to us, and the theorem that he proved that therefore give the name, why we use his name for the area, is he considered, it was related to a problem in logic where he wanted to find a large structure that was all behaving the same with respect to each other, and he could express the problem in terms of, you can express the problem in terms of coloring all the pairs of integers, and you put either a red edge or a blue edge for every pair. And he showed if you do this, not only can you find large subsets where everything's joined in the same color, but actually an infinite subset. Maybe here it would all be in red. You can find an infinite subset, everything joined in red. And of course, he did more general things where you could color hyperedges and you could use more colors. But this is the result we're going to focus on. And it's strange in a way. He started with the infinite version, but we're going to now look at a finite version. If I don't want to find an infinite monochromatic subgraph or clique, I just want to find a fixed size, I can ask, well, how many vertices do I need to guarantee a monochromatic clique of that size? Or the more general version, if you have 2 colors, you could say I want a clique of size K in red or a clique of size L in blue. And I could ask what's the minimum number of vertices I need to guarantee this. And the famous first example is if you want to have 3 who all know each other or 3 who all don't, then you can take just 6 people. If you invite 6 people to your party, there will be either 3 who all know each other or 3 who don't know each other. So you will always find a monochromatic triangle. And 6 is the least number of vertices, because with 5 vertices, you could have this coloring, and you will not find a monochromatic triangle. Okay. We got a bit, we got full of ourselves after we proved the results, and we got a T-shirt. You can see the. Let's get this party boosted. So it's got lots of people in it. It's called the party problem sometimes, because how many people do you need to invite to a party? Good. But we're going to focus on the general case, or K and L being large numbers, rather than thinking about 3 or 4 or anything. And there's a trick from the Ramsey result, where you get this infinite monochromatic set. You can use a compactness argument to say, if you just want a clique of size 100, then there will exist a finite n. Okay. So all these Ramsey numbers are finite. But the first really concrete upper bound was by Edish and Sekaresh 5 years later. And they proved, I put 2k choose k. Really, I guess it's like 2k minus 2 choose k minus 1. It's basically the same thing. They proved it's a bit, it's most that, which is just a bit less than 4 to the k. So you've got this nice exponential upper bound. And I think for a little while, people tried to do examples. People tried to create colorings where, you know, it showed you would need a large number of vertices. When you're proving a lower bound, your task is different, right? Your task is to show, I have this funny coloring, which doesn't have large subsets, cliques, all in one color. And I think people had just these funny examples that got up to polynomial that weren't really any good at all, until Erdos said, color randomly. So this is one of the first articles that really, you know, leads the way into probabilistic combinatorics, which has become a very important area in its own right. But at that point, it was not at all an obvious thing to do. In a way, this is exactly what David was talking about on Monday, because he was talking about the largest independent set in a random graph. Well, if a random graph, G(n)(1)2), you could just think of the edges as red as the non-edges as blue, and the independent sets are just the blue cliques. So it's really, this root 2 to the k is the same as saying you have independent sets up to size 2 log n. Okay. Now, yeah, this is, of the two sides, the upper bound and the lower bound, really the lower bound, which I think has a little bit more contact with probability theory in general, because there you're trying to make something. You're trying to make a large coloring without a particular type of structure within it. And because we turn out to be rubbish at actually making things, you know, with our hands, like really coming up with ideas, lots of these involve doing randomness at some point. And so yeah, we exactly have to find a coloring on a large number of vertices, coloring of the edges with a large number of vertices, so you don't have a certain structure within. And it's funny, I was sort of listing the different ways this could be done, or has been done for different problems, and there are at least 5, I think, really distinct ways it's been done. It can be just random, so as well as we saw in the Erdos example. It can be random star, meaning random, but you're using a bit of a weird distribution. You've twisted the way you're choosing things in some clever way. So even if you're doing random, sometimes you have to think about how am I going to do something a bit different, a bit clever. It can be random plus deterministic. I've got deterministic plus random, which is different, or just deterministic. So let's just give a quick example of all of these, just so I can show the type of variety of examples that you end up using for lower bounds. Pure random is what we just said, Erdosh's example. You take basically root 2 to the k, vertices, your n is about root 2 to the k, and you just color each edge red or blue by tossing a coin. And if the expected number of monochromatic cliques is less than 1, then obviously one of these colorings must have no monochromatic clique. If the average of a large collection of things is less than 1, and all these values are non-negative integers, then one of them is 0. Right? Random star. So sometimes you can do, so this is for actually off-diagonal Ramsey numbers. Lots of the best constructions are like this, or if you take like L to just be 3, so it's R3K, you can do a triangle-free process. You add the edges one at a time and say, I'm never going to make a triangle. So you've kind of twisted the distribution in a weird way. and they give the best lower bounds in some cases. Deterministic, random plus deterministic, sometimes you can generate this funny random coloring and you think, oh, I've done pretty well, but look what the randomness did there, I don't like that. And you come along afterwards and you just say, oh, you kind of correct all the little problems. So this is often a useful way to just tidy up the ideas, the random, or the little errors that have come in by it being random. Deterministic, I think, is quite self-explanatory. There's a case of how many people do you need to invite to have 4 who all know each other or 4 who all don't? Turns out to be 18 people. And the example that gives the lower bound is a coloring of Z17, where you color depending if the difference is a square or not in modulo 17. There's also other graph Ramsey problems where you have a Turan type example is the extremal. So that can come up as well. Obviously not for the cliques one, but there's variants of what you can look for where that's the answer. So let's get on to this missing one, deterministic plus random. And this is the one which was involved in a very major breakthrough last year by Matthäus and Verstuyt. Because, so our 4K, what's our objective here? We want to try and come up with some clever coloring which has no K4, let's say in blue, so this doesn't happen, it's not allowed, and doesn't have very large red cliques either, right? You're trying to limit the size of the red cliques. And previously, I think it was probably Peter, who's here somewhere, and Tom Bowman had k to the 5 over 2 times a certain polylog term, which comes from doing the K4 free process. And I was quite convinced those types of processes really ought to be the best type of construction you can do. But they did something quite different and really improved the bound hugely and got within a polylog factor of the upper bound. So they do something deterministic and then actually 2 random steps. They come up with a really clever projective plane type construction to define a graph, and then they basically take the parts of the projective plane and put a clique on each one and use it to define a big graph, and such that the only K4s are contained in one of these cliques. That's the property they have. And then they randomly replace all the maximal cliques by a complete bipartite in each. And then, of course, you kill all the K4s, right, in there. But you're not yet happy with the size of the independent sets, but you can at least count and show there's not too many large independent sets. And they do, so you do bound the number of independent sets of a certain size, of size k. And then you do an extra round of randomness, you reduce the number of vertices, reduce to an induced subgraph. And somehow this magically works. And a related problem, if you want to improve, for higher, R5K and all this sort of stuff, that we haven't got those constructions. And if you look through their proof, it really just depends on coming up with graphs that are, say, K5 free or something like that, and remain dense enough on relatively sparse sets within the graph. In other words, you zoom into a subset of a certain size, it doesn't get too sparse. So if you want an open problem, you could try this. So we're going to say a graph is, with density beta is dense on R sets if on sets of size R you maintain at least 1/10 of your density. Okay? And so my question would be, and I think, you can check this with their details as well, but I think this is enough to give an improvement on the Ramsey number of our SK. Can you find KS-free graphs with this number of edges, so this type of density, which remain dense even on sets of size root n? So you want it to have a certain density, and even on subsets of size root n not become too sparse. So with deterministic ideas or probabilistic ideas, or whichever they are, try and come up with one of these, and you can help advance the bounds. Okay, now I got some more funny pictures from, because everyone's, settled in, just feeling a little bit like they're dozing off, so let's have some funny AI pictures and at least laugh a little bit. I asked it to come up with things related to Ramsey theory. I may have said friends and strangers as well. This is a funny one. I don't have too much to comment on them. They're just kind of a bit weird. That could be useful, maybe. We could see if we can use that. Yeah, okay. Yes. Friends and strangers, I don't know. The next one's a bit bizarre, I think. That's a bit bizarre. I don't know what's going on there. And that's nice and colourful, so everyone's feeling good again. Everyone's feeling good again. So this is what the computer overlords have deigned to give us in terms of pretty pictures today. Okay, so now we're going to go back to our Ramsey problem and think about the upper bounds. So the upper bound, your challenge is completely different. You want to say, I've been given this vast, vast, vast coloured thing. I've got a red or blue colour for every edge in this vast, 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 vast graph. I need to somehow show there is a large monochromatic clique somewhere. I'm kind of searching around trying to find it. And, well, the first thing I'll say, yeah, is a general overview or general idea to have in your head is you come up with an idea, I'm going to try and find it like this. And you kind of have to declare it. This is my idea. This is how I'm going to try and find it. And then at all points thereafter, you kind of have to assume the coloring has been invented by your enemy to be the worst thing it could be. So just have that in mind each step. We're just given something new. We don't actually have much control over it, other than that which we've directly defined by our choices. Okay. So there were some improvements. Thomason, I guess roughly 50 years after the original result, I managed to improve the upper bound by a factor of root k, and he actually sort of laid out a general method involving quasi-randomness that could potentially lead to bigger improvements, and the details of that were fleshed out by Conlon and later Saar, and they sort of managed to fully implement the idea he suggested. And the improvements, yeah, were then, you're basically winning e to the log k squared. Okay, Conlon has over log k. Finally, you get e to the constant log k squared. And what's even better, maybe, is to win actually in exponential terms. So our result, we can state, our theorem will be that we managed to improve, in fact, the base of the exponential, so you win by an exponential factor. Breaking news at the end. Well, there's some breaking news, you know. So there may be some news about the constant here. So let's think about the Edler-Sekaresh bounds. This was the first concrete upper bound, and it was actually very good, relatively speaking. You know, it took a lot of work to improve on it, and yet it's very simple. It's about the simplest argument you can imagine in some ways. So you're going to use induction. We're going to try and prove this upper bound. Okay, there's some base case, that's fine. And then you note that this is the sum of these two binomial coefficients, doing -1 or -1 on both. That's just the identity that we know. And so you have the following thing. You look from the point of view of one vertex. Either he has at least this number of neighbors in red, right? And if he has this number of neighbors in red, then by the induction hypothesis, that's at least the RK-1L. And so that means you can find either K-1 clique in red with that guy, you'll complete it, or you can find a blue KL and you're just done. Okay. And in the other case, well, you have less than this, and then you just use your identity. If you have less than this and you're in red and your total is that, you're going to have at least that many in blue. Okay. So you can just do the argument in blue instead. Okay, so you'll have at least this many neighbors in blue, which is at least the Ramsey of k in L-1. And so you either find the red clique size k immediately or L-1 in blue, which together with that guy, you win. Okay. So it's very elegant, even though, and it's very simple, and it was pretty good as well, really. So what were the improvements previously on the upper bound? There was sort of this idea, yes.
So that procedure is also very simple and algorithmic, right? That one can implement it?
Yes, I would have thought so.
Others are also that sort of implementable?
They're all kind of algorithmic. I don't know, yeah, you'll see with the ones I'm about to present that there may be extra challenges. Although I think our final one, it's not so, yeah, it's not so complex really. There may be some counting things of like, I don't think it's super complex in terms of, they're all written in algorithmic style, I guess. The idea with the improvements is sort of, what happens if you, I think there's a natural thing, maybe I should just say this first. In a way, if you could just keep doing steps of the same color, that would seem much more efficient, right? Because you're trying to find either in red or blue, and kind of implicit, if you actually apply that induction, you might be doing a red step, and then a blue step, and then a red step again, a blue step again. And so you feel like you ought to do better if you could do more steps in the same color in a go, right? And so you could try and do their argument, but be doing more steps at once. And if you just want to do 2 steps at once, then what you're really doing is saying, I want to take in these 2 vertices into the red clique I'm building or something. And I still want to have a good number of vertices that are neighbors of both of these. And so you're really just looking for a pair which is in lots of monochromatic triangles. That's what it turns out to be. And you can do this with Goodman's formula. So this is what Thomason did in the 1980s. Basically, he showed you could always find an edge which is in many triangles. I won't go through the details. This is just a relatively elementary graph theory thing. You can find an edge in many triangles, and so you apply this in the red graph. You can find a red edge in many red triangles. And you basically, that will already give you a way to do 2 steps at once, as it were. You relate it, instead of relating it to k minus 1, you're going 2 steps. And if you just had your usual Ramsey bound on, this should be RK, oh no, yeah, RKK is at most, yeah. So if you have a usual Ramsey bound on this guy, you get a slightly better bound than before, but you only win by a factor that looks like this, which is not very good at all. We want to win a much bigger factor than that. But you can kind of keep applying the same thing again and again and again, k over 2 times, and then you win a constant multiplicative factor, which is something, but still not so amazing. But then you realize you can do this on different logarithmic scales, because you've gone down to half the size, you can do it again. You go down to half the size again, you can do it again. So you basically get to win this constant log k times, which is like winning a polynomial. Okay. And Thomason actually shows you win a root k. But this is the idea, you win a polynomial. And how about if you do some larger number of steps all at once? Well, you first run into an obstacle. If you try to do 3 steps at once and you want to use the same method, then you want to know there's lots of monochromatic K4s in the graph. And there's no Goodman's formula. In fact, there is a funny coloring, also due to Thomason, where you get fewer monochromatic K4s than sort of the expected value. So that kind of ruins that very direct approach. And so he suggested this whole more complex analysis with quasi-randomness to try and correct for this. And I'll probably go quickly through this because we want to say something about the other stuff. But Conlon managed to sort of implement this with doing a relatively large number of steps at once, log k over log k. And Saar in 2020 managed to improve and get doing log k steps at once. And you go and you do the calculation, and it gives exactly that improvement they were saying, e to the log k squared. Okay, so let's jump on to our result is we can get an exponential improvement on this. Here are, I didn't say my co-authors, it's with Marcelo and Rob and Julian. But, I always like to put up slightly more embarrassing photos than this. So, we've got carnival pictures. I didn't have a carnival picture of Marcelo, and so we have him on the beach with the dog sniffing his head, which, there you go. It's all good. It's all good. So let's think about this challenge now. We want to try and improve, we want to be much more efficient, and how are we going to do that? And it's really coming back to the idea I sort of touched on, which is you kind of want to do more red steps or something. It involves this idea. When I was doing lots of red steps at once, I was kind of finding a large set that was all a clique in red, and quite a large set over here, which just joins in red to the clique. And such a structure is called a book. And we're really asking, what size, can I find a decent sized clique? And such that this set over here, they're like the pages of the book or something, the vertices that join just in red to the clique. If that's bigger than the Ramsey k minus t, then immediately you find what you want. Because you either find the blue clique of size k here or k minus t in red, and you join it up. So, yeah, and this is, I should say this is related as well. Yeah, it's related as well to the idea, doing lots of steps in the same color, you begin to really win something. And we'd actually like to do that where the number of steps we're going to do in the same color is actually of the order of the total thing we're finding. Maybe it's k over 100 or something. So then you really have a chance of winning an exponential factor. And strangely, our approach works better off the diagonal, or in other words, where the k and l aren't equal. And there, yeah, so Erdős-Szekeres says this. It's useful to have a slightly different parameterization. This is basically very close to being gamma to the minus L, 1 minus gamma to the minus K, where gamma is this ratio, L over the total. So this is the equivalent, this would be 4 to the K in the diagonal case. And what we're going to do is we're going to win a small exponential factor in L relative to that Erdős-Szekeres bound. So we'll try and give the idea of how we get that result. How you get to the diagonal is like a bit of a twist and a bit of a gambiarra, it's called here. It's like a dodgy bodge job that just is lucky it gets there, and thank you to your chosen deity for allowing that to be the case. So let's start with the Erdős-Szekeres algorithm, but I'm going to say it in a slightly different way. You can get that slightly weaker bound that's basically the same, but by actually fixing at the start what would be your choices, depending on density. So you'll say, I'll do a red step if, maybe this is back in the diagonal case, sorry. You can say, I'll just always choose whichever one is larger, right? If I have more red neighbors, I'll go into the red neighborhood, and then I'll pick a second vertex in there. If it has more blue neighbors, I go to its blue neighborhood. Then I pick a third vertex in there. If it has more red neighbors, I go to its red neighborhood. And you can see this as generating a clique in red, because if you just take all the red vertices, they're going to be joined in red, and a clique in blue, because if you take all the blue vertices there, give you a clique in blue. And the remaining set, the sort of candidates to join later, you just lose a factor of 2 each time, so it has at least this size. So, yeah, if you manage to just do red steps, you'd be doing very well. The same thing in the off-diagonal version actually looks like this. So you're doing a red step if it's density at least 1 minus gamma, and a blue step if it's at least gamma. I mean, you can choose to do this for any gamma, but it happens that the optimal gamma is the one we said at the start. Okay. Now, that says if your original n is bigger than 1 minus gamma to the minus k, gamma to the minus l, you can just check that means the process survives long enough. So let's just try throw out ideas. How do we find this large red book? We want to find a large number of vertices in red, all joined in red, and such that on the other side of the book, the set of vertices that's still adjacent in red to all of them, you have a very significant number. Right? This is actually enough in this case that it's bigger than the Erdős-Székely bound, and so therefore you definitely know how to complete the argument. Okay. So why should there be a very efficient way to find this type of structure? Well, there's no good reason, right? But let's try something. And again, yeah, it's going to be an algorithm. But let's arrive at we're really just going to arrive at the idea, right? We're not going to start, I'm not going to if I put up the algorithm, then we're going to spend a lot of time going, oh, this is the detail of every step, and it's not going to quite work. So let's do the storytelling version, which we're going to do via just saying our first idea. If we just say our first idea, then you'll tell me it's ridiculous. And I'll say, well, then I'll change it in this small way, and then we'll see where we converge to after a few steps. So this is naiveness level 4, very naive idea. So I just want to build this big red book. I'm going to draw it like this, where we're going to think of X as the candidate vertices that could in future join the clique. And Y, so imagine just at the start of all time, you just split the vertices in two. Okay, you just do a partition of the world into two. And so you've got half the vertices on each side. And you're going to do something like the process we were talking about to build a red clique on the left. And who are the future vertices that could join the clique? Well, they definitely have to just join in red to the clique, right? If you want to be a future choice that you could add here. And on the other side, we just track who over here is just joined in red to the clique. And we'll call this set Y. Okay. And our objective is to go and do this for a long time, such that the clique gets to be big and Y hasn't shrunk too much. If Y is just going down by the factor it's supposed to every time, we'll easily get an exponential improvement. Okay. So here's my super naive idea. Instead of this Erdős-Székely thing where I decide, do I want to do a red step or a blue step, I'm just going to insist. I'm just going to do red steps. Now, I need people to tell me why I'm stupid. Does anyone see why I'm stupid? Surely someone knows why I'm stupid. So, there may be, so if inside X, this was all very blue, remember, your enemy can come up with whatever they want at each stage, really, subject to the conditions you've defined, right? So he could just say, inside X, it's now all blue. So what happens? I maybe add V to A, and in the next step, there's no X left, and the process just ends, right? So that could be bad. That could be bad. So if X becomes very blue, then the process ends quickly. So we need to adjust for that. So we improve it a bit, and we say on the left-hand side, we're now going to kind of be doing the whole Erdős-Székely type argument. If it gets very blue, you do a blue step instead. If it's reasonably red, then you just do a red step. Okay? And, I guess in vaguely algorithmic ways of writing things, you write it like this. So if it's a blue step, you update. You don't need to update A or Y. They just stay the same. You put a vertex in B, and you restrict X to just the red neighborhood of that vertex, or blue neighborhood of the vertex. And in red, it's a bit more difficult. You have to add to V. You have to restrict X and Y to be the red neighborhoods. In that case, B doesn't change. But this is still stupid. Yes?
I think I'm stupid because I didn't understand the difference between X and Y. Can you explain it?
So it's sort of at the start, it just seems a bit arbitrary, but we just say, at the start of all time, we are just going to split the vertex set in half. A random bipartition, if you like. Okay. And on the left, we're going to try and, we'll end up doing, as I say, this thing that resembles the old Erdős-Székely argument. But this introduces an asymmetry between the roles of X and Y. When I do a blue step, I will have to restrict X to just join in blue to B. Whereas, because I'm not going to make that I'm not going to demand that of y. So y, I will only shrink it when I do a red step. So that changes they're not completely symmetric. The way you do it, you just do a random bipartition at the start. But the reason that they're different is because I want to keep this as large as possible for as long as possible. So I don't really want to restrict it on the blue steps. Okay. But it's still very naive. Yes, Mickey?
The gamma we should think of as a constant less than a half.
Gamma is probably, a constant less than a half, yeah. Certainly the way we first wrote the article, it's better if it's a constant than going to 0, but all the results will work if it goes to 0. But just think of it as a hundredth or something. Okay. So we're doing either k in red or k over 100 in blue. Okay. But this is still very naive. Why is this very naive? Well, I mean, you can do it, but it's very naive to think this is actually going to work and be useful because we want to keep y very large throughout the process. We want y to be the other side of the book. We want it to stay large. Now, when I do a red step, I need to restrict y just to the red neighborhood of v. And in the current algorithm, I haven't mentioned that at all. And so maybe v just joins in blue to y, right? And so you just kill y in one step, and then you haven't achieved anything. Well, if you're not quite that stupid, you could say, well, I'm at least going to choose a vertex with at least average red degree to y, maybe. But then it still depends on the behavior of the density between x and y in the process. Okay? So if you don't pay any attention, then you can call P the current red density between the two sides. You can certainly select a vertex, with at least average degree. But over time, the red density could fall. So this isn't so disastrous as the things we've said before, where you just do one step and you're dead. But maybe slowly over time, the red density gets less, and you're not going to be proving a bound on Y that's good enough. So this is where you get to the following moment. Orange is like less red than red, right? So a thing which is a little bit bad, not completely terrible, but a little bit bad, is you're going to do this red step. You've got the red neighborhoods on the two sides. You're ready to do the red step. Maybe these red neighborhoods are big enough. You're very happy with that. But it's just a little bit sparser in red. In other words, your red density will go down if you do this step. Well, remember, this on the left-hand side, if like Mickey was asking, what's the size of gamma? If gamma's 100th, then the 1 minus gamma is like 99 over 100. And that will be roughly the red degree in general. So this red neighborhood is actually 99% of the left, maybe. And the blue neighborhood is maybe 1% of the left. So if you're sparse in red from 99% of the left to this set, then this 1% has to make up for all of that, right, to get back to the average. So you're actually far denser between this small set and this set on the right. So it offers you at least a choice. You can do the red step you were intending to, and accept losing a little bit of density, or you can do this completely different step, which we're going to call a density boost step, which is sort of like a blue step from the point of view of the left. You do a blue step, but you also do restrict y, and it manages to get you a density boost at the same time. And then, so you're going to put this in an algorithm, you just have to make a choice. You say, I will do that red step if it costs me like alpha. And let's see, say you're willing to do it if it costs you most alpha, if your density is less than p minus alpha, then it gives you a certain inequality about how big the density needs to be in the other part, which would be like p plus 100 alpha in our example, which is a lot, right? You're winning 100 times more than what you'd lose in the other case. Good. So now we're getting there. We basically have these two steps I won't talk about too much, but there's a reason why when you do a blue step you don't just do one, you do a lot, and there's a reason it's useful to throw away low-degree vertices, but let's not worry too much. So our idea will be we want to do a red step if the red density doesn't go down too much, if it's at least the current density minus alpha, do a red step. Otherwise, we do a density boost step. Okay. So it seems like I've gone through so many different levels of saying I'm less naive. How could I still be getting it so wrong? Okay? Because this still doesn't work. It still doesn't work. So why does it still not work? Well, we need to think about what's the choice of alpha. How much density do we accept to lose at each step? So if on every step you're losing alpha, and over time you want to do order k steps, you don't want to lose like half of your density. That sounds pretty bad, right? So you'd like alpha times k to be small. Because if you keep doing these red steps and losing alpha, you don't want to lose too much density over the whole thing. Okay. But if your alpha k is very small, then your enemy could just say, I'll give you that boost step. Oh, I'll give you that boost. I'll give you the boost. And he's giving you 100 times alpha, maybe. But even so, if alpha k is really small, 100 times alpha times k is very small, and so he'll keep giving you the boost, and the density doesn't really go up by much. So you haven't actually achieved anything. You're never doing the red steps. You're just carefully increasing your density by a small amount and never using it. So that's kind of useless. So we've gone through all these steps of trying to be less naive, and it's still kind of useless because our alpha doesn't make any sense. Luckily there's a solution. So we take inspiration from our friends, the bankers. Our friends who are bankers presumably sit around all day saying, my investment has gone up by 10%. Haha, your investment has gone down by 10%. In other words, it's all in the language of proportions, right? Going up and down by a certain factor. And in that spirit, you might say, okay, there's kind of two cases. If your density is close to where it started, or maybe even below where it started, you really don't want to lose any more. You're kind of a poor person in this respect, you see. So you're not going to bet very much on each step. You're not going to accept to lose very much density on each step. So you put your alpha to be like an epsilon over k, a tiny, tiny epsilon over k. If your density's gone way up, then you're sort of like a rich person, right? You've got way more density than you started with. You think you're doing pretty amazingly. So why don't you bet a positive proportion or some epsilon proportion of everything you've won so far? So what you accept to lose in density is this little epsilon times everything you've won so far. And okay, technically you can just put the alpha to be the sum of these two. I mean, or really you could take it to be the max. It would be the same. And what does that mean? Why does that suddenly save us? Why does that suddenly resolve all the problems with the alphas? Because our fear was that our enemy could just keep giving us the boost steps. And we wouldn't go anywhere. We wouldn't do anything. But now, if he keeps giving us the boost steps, because you're betting more every time, the more you've gone up, it's only logarithmic time before you hit density 1. And so he can give you, okay, log k steps, and you get to density 1. Well, then you say, well, I've got density 1. Of course I'm going to win. You know, you win by a lot. So weirdly, this kind of solves the whole alpha problem. And we probably don't need to do the details of the calculations, but you can say, if I've done this algorithm, I've done a certain number of red steps, a certain number of blue steps, a certain number of boost steps. Pretty simple inequalities here about the size of x and y after that. You need to think about this whole density. We call it the zigzag, because sometimes the density goes up, sometimes it goes down. You need to think about that in detail in order to get an inequality relating the number of boost steps to the number of red steps. The idea is, if each boost step you go up by 100, to compensate, you need to do 100 red steps, right? If you go by 100 alpha in the red steps, you go down by alpha. So you can control the ratio between those two, and that gives you an inequality between S and T. And when gamma's small, it's not too difficult. I mean, it would be like another half an hour and some boring details. But you can go through it and see, really, you can take T. This is of order K. I think it ends up being about 2/3 K or something. You run it until you've done 2/3 K red steps, and you can check the numerics of it, and your Y will be large enough that you can find the rest in the rest just using the Edor-Sekresh argument. So that's the idea of how you get an exponential improvement far from the diagonal, like that. And the diagonal is a bit more work and a lot of luck. The idea is you try the same approach. The bad thing about doing exactly the same approach is that now your densities in red and blue are exactly a half each, or basically a half each. If the density originally is much different from a half, you can already win an exponential factor for another reason. So let's assume it's basically a half and half in densities. But now you don't get the useful effects. When Mickey was asking about gamma, and I said maybe it's 1/100, and then I said, well, the red neighborhood then is about 100 times bigger than the blue neighborhood. That was very useful, because it says your boosts are really big and you won't need to do many of them. But if the red and blue are the same size, then you just have minus alpha or plus alpha. And you end up needing to do maybe as many boosts as there are red steps. It doesn't work out nearly as well. As a sort of artificial thing, you can weirdly change the rule about when you accept red and blue steps, even though the density is probably a half. So we do that, put it 2/5. But even so, we only get to prove the Ramsey numbers are most 4.04 to the k. And no one wanted a proof that Ramsey numbers are at most 4.04 to the k, apparently. So that was a bit depressing, right? That was a bit depressing. But then you think, well, what was that argument? The argument was you run this algorithm, which you call the book algorithm. You find this big book. And what you wanted is we wanted this to be bigger than this Edor-Sekresh number so that you could find the rest of what you wanted, right? And then we failed, and we just got this silly bound. But then you remember, this is off diagonal. And we've already seen a proof that you can improve the off-diagonal Ramsey numbers. So because you win here, whatever it was, then you win just enough there that you can find enough. So it's very lucky that works, right? It's very lucky that works. But because you do have the off-diagonal result, you can just about make it work. And in the article, we have a funny picture that looks like this. This is not AI. This is my own hand. Believe it or not. The picture basically means, even though the enemy has complete freedom about what they do, there's only really two parameters of the enemy's behavior that matter. It's how often it gives you red steps and how often it gives you boost steps. Because within that, you're basically assuming everything is worst case within those parameters, right? So he kind of just has a two-dimensional set of options for what he does, the enemy. And you can basically say, if you're in this blue set, then you would fail to win on the left with the Edor-Sekresh argument on the left. And if you're in the red set, you would fail to find the book you need. But because you just need to win in one way or the other, you just want that there's no intersection, right? If there's no intersection, then one of your two arguments will always win. And we have a conjecture which looks more probabilistic, which was what we spent 4 years working on before we suddenly just decided to go off diagonal, everything worked. So we spent, if anyone's a probabilist, which is most of you, you can maybe just take a picture and then solve the problem, and then we can write another paper Maybe it could even give better bounds. But basically, your xd is sort of a random vector in high dimensions. Isotropic is just a condition to do with the way the directions relate to each other. We want it to have sub-Gaussian, so it doesn't have too heavy tails. And this weird unbalanced property that, from the point of view of a random point, like 2/3 of guys want to be on the other side. If it was all random, then you'd have something maybe inner products with me would be roughly Gaussian, and so half would be on each side. But it's for most people, like most of the vertices hate them, right? They're on the other side. Vectors, sorry. And we just don't think this exists. So we want to show that this type of sequence does not exist. So if anyone's good at high-dimensional probabilistic geometry, then tell us why.
What's explained?
Just two independent copies of the same thing. I mean, I'm saying this, and I'm not really explaining what it has to do with the original problem. It's basically to do with the bad situation in our previous attempt. We were trying to do density boost in a different way. So either you manage to do a step without losing too much density, or you could show there's this weird situation where all of the red neighborhood, or most of the red neighborhoods are kind of pushing away from each other. They kind of have a negative inner product in that sense of. So it feels like there must be some weird structure happening if 2/3 of pairs of neighborhoods are pushing away from each other. And we should be able to use that to get some other structure. And this is one type of statement testing. I mean, it's not that we can, if we have this, we don't immediately have therefore ... and get a bound. But it's an interesting, I think, in its own right. Breaking news. So I said at the end we'll come back to the breaking news, which is from a different group, actually at McGill, and they've got 3.8 to the k, which is, well, they're Parth Gupta, Nadaimi Nadei, Sergey Norin, and Louis Wei. And, well, they put the name of the article as optimizing the CGMS bound, which is our bound. Now, it's all in the same similar setting to the way we work, but I think there are some new ideas there. In particular, in the off-diagonal case, they managed to write it as an inductive argument. And, you know, there's definitely something new there, as well as, you know, okay, they've taken a lot in the same setting. A lot of the steps they do are similar to our steps. But it's definitely, yeah, pushed it in some interesting ways. And so it's very good to know, you know, you can get this far with those bounds. Okay. How? So similar setup, as I said, and you do an inductive argument. At least for the off-diagonal part, you can do an inductive argument. And it's all based on the surplus. So you basically say, if I have a certain surplus of red edges between the two sides, then I can guarantee either the red clique or blue clique the way I want. And you basically do something very similar to what I was saying, you have more here or you have more here, and you use that in an inductive way. Yeah, I mean, probably look at their paper if you want to see the details. Very cool. And I think that's all we have to say, with a final picture at the end. Okay. I mean, I was slightly surprised they got 3.8. I'd kind of thought maybe it would be around 3.9 or something. I mean, there's not like a number. Yeah, I would be surprised if it goes a lot further than that. I mean, there's reasons why, for example, if you want to really push it, you can't get anywhere near 2 or anything crazy like that, right? I should say, from the point of view of probabilists or even intuition in general, I mean, the root 2 to the k has something very natural about it. because you do the random graph, you do the random coloring, that's what you get. 2 to the k is also a very natural possibility, because if you think about just trying to find, if you're trying to find the clique locally, but what you see actually continues to kind of be random, you should, you'd maybe think, okay, you do red or blue, okay, it probably continues to be half and half. If there's some randomness in how you're choosing a vertex as well, and you're not in this enemy situation, things are actually reasonable, then you just go into red neighborhood every time, and you get a half, a half, a half. So 2 to the k is a reasonable thing to believe as well. I always felt it was less easy to believe things bigger than 2 to the k, but I don't, it would be a completely different proof by a long, 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 long way to get anywhere close to that, obviously. Yeah.
Can I ask a quick question of historical interest, I guess? Well, you presented your approach as a series of less and less naive strategies, right? Is that how you guys came up with it, or is it kind of... Because, I mean, even though, the first few approaches are maybe not ideal, it still looks very tidy, right? So I would think.
Yeah, so I think the more historical connect, there was a good bit of that. There was a good bit of, we'll try this, we came to an algorithm within maybe a month of working it, it was 5 or 6 years ago, that had quite a strong resemblance to what we ended up doing. But we were much more in the mindset of trying to do it on the diagonal, and this particularly simple trick to get the density boost doesn't work. You can just kind of see it's not going to work. So we wanted it for a different reason, which is to do with that conjecture, this idea. We were going to accept even very small steps in red, because we weren't going to do as many of them. We just wanted to do linearly many for some small number. And you just wanted, even with going into a small neighborhood, that the neighborhoods weren't too anti-correlated, as it were, 2 points, because that's what decides the updated density, right? And so we kind of had this picture on here. The bad case, the case in which we can't work, is when a good majority, like 2/3 of the pairs on here, have red neighborhoods that are significantly anti-correlated with each other. And we thought that's a lot of structural information. And there should be some way to use that to find a much denser subgraph and get sort of a dramatic density boost. And if we had something like that conjecture, maybe we could. But that conjecture comes out of just sort of looking at the bipartite graph and saying, let's throw a lot of linear algebra, look at it in terms of eigenvalues and all this stuff. And it turns out to be a problem in terms of points in space, or on spheres or whatever, and therefore you can phrase it like that. But there was definitely a good amount of naiveness. My colleague Rob, he kind of has this strange genius of just being able to keep coming up with ideas, and he wouldn't mind me saying, they almost always fail, but you go through enough of them, and you've really learned something very important. There's kind of, that was part of the story, I think.
So it is probabilistic at the end, right? The Broken-Tally lemma.
Exactly.
Any more questions? If not, let's thank Simon again.